Welcome to my video on galaxy classification. In the video, I will look at how galaxies are classified. When you begin imaging galaxies, you quickly notice that they don't all look the same. Some show spiral arms, others appear smooth, and some look chaotic. Astronomers developed a system to organize these shapes, and understanding it will help you interpret galaxy images. There are billions of galaxies in the observable universe. Every deep field image taken by modern telescopes reveals thousands of them packed into a tiny patch of sky. Each of those faint smudges is an enormous system of stars, gas, dust, and dark matter. Galaxies differ dramatically in size, brightness, structure, and star content. Some are graceful spirals with well-defined arms. Others are smooth and rounded, with little internal detail. Some appear chaotic and distorted, shaped by gravitational encounters. To make sense of this enormous variety, astronomers created a classification system. By grouping galaxies according to their visible structure, they could begin to look for patterns that might reveal how galaxies form, evolve, and interact over billions of years. In 1926, Edwin Hubble proposed a system for organizing galaxies based on their visible structure. This diagram, known as the Hubble Tuning Fork, groups galaxies into three main categories: elliptical galaxies on the left and two branches of spiral galaxies on the right, normal spirals and barred spirals. The diagram resembles a tuning fork, which is where it gets its name. It is important to understand that Hubble did not intend this to represent an evolutionary sequence. Rather, it is a structural classification, a way to organize galaxies according to what we observe in their shape and features. What you are seeing here is Messier 87, a giant elliptical galaxy located in the Virgo cluster. Unlike spiral galaxies, M87 has no visible spiral arms, no dust lanes, and no distinct internal structure. Instead, it appears as a smooth, rounded distribution of light. That smooth glow comes from billions of older stars packed into a roughly spherical shape. Elliptical galaxies contain very little gas or dust, which means there is almost no new star formation occurring. M87 is also famous for its supermassive black hole at the center, the first black hole ever directly imaged. What you're looking at here is a classic spiral galaxy, Messier 101, often called the pinwheel galaxy. Notice the flattened disk structure and the bright central bulge. Extending outward are well-defined spiral arms, rich in gas and dust. Those bluish regions along the arms are areas of active star formation, where new stars are being born. The darker streaks you see are dust lanes, silhouetted against the brighter starlight behind them. Spiral galaxies like M101 are rotating systems, and their structure tells us that star formation is still ongoing within their disks. What you're looking at here is NGC1300, a classic barred spiral galaxy. Notice the straight bar of stars stretching across the central region. Unlike a normal spiral galaxy, the spiral arms do not begin at the nucleus. Instead, they emerge from the ends of that central bar. This bar structure plays an important role in the galaxy's dynamics. It helps channel gas toward the center, often fueling star formation and sometimes feeding a central black hole. Barred spirals are very common in the universe, and our own Milky Way is believed to have the same structure. What you are looking at here is the Large Magellanic Cloud, a nearby irregular galaxy and a satellite of our Milky Way. Unlike spiral or elliptical galaxies, the Large Magellanic Cloud has no defined structure. There is no central bulge, no organized spiral arms, and no smooth elliptical shape. Instead, we see a patchy, uneven distribution of stars and gas. Those bright regions scattered throughout the galaxy are active star-forming areas, including the famous Tarantula Nebula. Irregular galaxies are often shaped by gravitational interactions, and in this case, tidal forces from the Milky Way have influenced its structure. What you are looking at here is the Sombrero Galaxy, also known as Messier 104, a classic example of a lenticular galaxy. Notice the large, bright central bulge and the thin disk structure surrounding it. However, unlike a spiral galaxy, there are no visible spiral arms extending outward from the center. Lenticular galaxies are considered transitional objects. They have a disk-like spirals, but they contain very little gas and dust, which means star formation has largely stopped. You can think of them as spiral galaxies that have lost the material needed to form new stars. leaving behind an aging stellar population. What you're looking at here are the MICE galaxies, two spiral galaxies in the process of gravitational interaction. Notice the long, thin tidal tails stretching away from each galaxy. These are streams of stars and gas pulled outward by powerful gravitational forces as the galaxies pass near one another. Over time, interactions like this can dramatically reshape galaxies. Spiral structures may become distorted, gas clouds can collide and trigger bursts of star formation, and eventually the two galaxies may merge into a single, larger system. Many large elliptical galaxies are thought to have formed through mergers like this over billions of years. What you are looking at here is the Andromeda galaxy, Messier 31, one of the most popular targets for amateur astronomers. When you understand galaxy classification, this image becomes more than just a beautiful photograph. You recognize it as a massive spiral galaxy with a bright central bulge, a rotating disk, and regions of ongoing star formation. Knowing the difference between spiral, elliptical, lenticular, and irregular galaxies allows you to interpret what you are seeing in your own observations. It turns astrophotography into a deeper understanding. Thank you for watching, and I hope this overview helps you appreciate the galaxies you capture in your own night sky.